Hi everybody, and welcome to example 2. We are looking at the top of page 40 in the workbook here. Let's take a minute just to read this example together. So they're telling us that the fluid pressure in atmospheres at the bottom of a body of water of varying depths is given by the formula P of xy equals 1 plus x squared y over 100, where x and y are measured in meters. Okay, so just to help you picture this situation, let's maybe draw our body of water up here. And kind of the way you want to think about this is that this is a lake or something where the depth is varying. So if you're sitting at a point on the bottom of the surface and sort of moving around the bottom of this lake, as you move around, you might find that the depth of the water increases, so you've got more water above you, and therefore this pressure that we have is going to increase. It's going to increase and decrease depending on how much water you have above you. Okay, and so they're asking us to do some calculations, and this will be a nice opportunity just to refresh our memory on some of these concepts like directional derivatives and gradients. All right, so let's start with part A here. So they'd like us to do two calculations, starting with our calculation of the gradient. Okay, so reminding ourselves of what that is. Okay, the gradient is just a vector that we get by taking the two partial derivatives as its components. Okay, so the derivative with respect to x in the I direction plus the derivative with respect to y in the j direction. Okay, so we need to calculate two directional derivatives, and our function, two ordinary derivatives. Our function looks like 1 plus x squared y over 100. So what would the derivative with respect to x of that be? Okay, well, the 1 plus part's going to go away, and then if we take the derivative of x squared, we're going to get 2x, and the rest of that's going to kind of come along for the ride. So we'll get 2xy over 100 I. Okay, and then the derivative with respect to y, same idea. Go back over here, and we take the derivative of that, the 1's going to go away, and the derivative of y is 1, and the rest of it's going to come along for the ride. Okay, and I'm just going to simplify a little bit here. So if we take the 2 and cancel it into the 100, we're going to get a 50. So we could write this as xy over 50i plus x squared over 100j. All right, so now that we've got a formula for the gradient, let's find the gradient at 1, 2. That's our point of interest here. And all we really have to do there is substitute the numbers 1 and 2 in for x and y into the formula for the gradient that we got there. So if we do that, we're going to get x times y, which is 1 times 2 is 2 over 50i, plus 1 squared over 100 is 1 over 100j. Okay, and again, I'm going to do a little simplifying. 2 over 50, we could reduce down to 1 over 25. So let's rewrite that just as 1 over 25. Okay, and they also asked us for an interpretation of this. Okay, at the end of this problem, we're going to write a nice, thorough interpretation, but let's just think conceptually about this right now. What does the gradient vector represent again? Well, we could say that this just points us in the direction of maximum pressure increase. Okay, in particular at the point 1, 2. Okay, so there's where we are so far. And then the second thing that they'd like us to calculate is the magnitude of the gradient. Okay, well, all we have to do there is to just take that gradient vector that we calculated and find how long it is. Okay, so we're going to take the square root of the sum of the squares of our components. Okay, let's try that again. So 1 over 25 squared plus 1 over 100 squared. Okay, and if we get a number for that, that's about, we rounded off, 0.041. Okay, and you might remember the magnitude of the gradient gives us the magnitude of the greatest change. So we'll say it this way, the magnitude of the maximum pressure increase. Okay, and we could, as long as we're at it, maybe think about units here. Okay, what units would the magnitude of maximum pressure increase have? Well, notice that pressure is being measured in atmospheres, and this rate of change is with respect to our motion in meters. So this should have units of atmospheres per meter, and of how fast the pressure is changing as we move in the direction of maximum change. Okay, and now for the interpretation. We've kind of already gotten started with an interpretation, but we'll make it a little bit more specific down below. So we'll start by reminding ourselves that all of this is happening at the point 1, 2 on the bottom of our body of water. Okay, and the first part is the gradient. Okay, so that's telling us where we're getting the fastest increase. So let's say it this way. The fluid pressure will increase the fastest if we move in the direction of the gradient, which is 1 over 25I plus 1 over 100J. I'm just recopying the gradient that we calculated. Okay, and the second part of it is if we move in that direction of maximum increase, we're going to get 0.041 atmospheres per meter as our rate of change. So it will increase at 0.041 atmospheres per meter. Okay, so there's an interpretation of the two quantities that we calculated in part A. We are ready then to move on to part B. Let's see what they're asking us here. So they'd like us to find P sub u at 1, 2, and remember that notation just means directional derivative of the pressure in the direction of the unit vector u at 1, 2. Okay, and actually, I'm sorry, I didn't read the rest of the question here. U is a unit vector in the direction of 3I minus j. Okay? So, we need to use our formula for the directional derivative, and there are two pieces to that formula. There is the unit vector that we're going to move in. So, first thing we need to do is to find a unit vector in the direction of 3I minus j. Okay, so there, we're just going to take 3I minus j and divide it by its length, which is the square root of 3 squared plus negative 1 squared. Do the algebra there, and you're going to get 3 over the square root of 10I minus 1 over the square root of 10j. Okay, and the other piece is the gradient vector, but we already calculated the gradient vector up here in part A. Okay, so we can just use that. And so the directional derivative that we're looking for is just going to be that gradient vector dotted with the unit vector. If we put those two pieces together, that's going to look like 1/25 I plus 1 over 100j dotted with the u that we just calculated above, all right, and then the rest is just kind of doing the calculation and seeing what we get. Okay, so 1/25 times 3 over the square root of 10 plus 1 over 100 times negative 1 over the square root of 10, and the rest is really a job for your calculator here. Okay, if you punch that in, get a decimal, you're going to get about 0.0348. What would the units on that number be that we just calculated? Okay, well remember, this is a rate of change. Okay, we're measuring the rate of change of pressure, so this should have units of atmospheres per meter. Okay, and that's telling us how fast the fluid pressure is going to change if we move in this direction up here.